We're in for a treat because we have a astrophysicist from Northwestern University who came all the way to Fort Wayne to give this presentation tonight. And her name's Kari Frank. She trained at Purdue with uh, Ben, and he is going to give a formal introduction.
Okay, so tonight's speaker is Kari Frank, who, as Mike said, I knew her back at Purdue. We were at Purdue together, where she put up with my antics. After Purdue, she did her PhD, finished in 2013, right? Finished her PhD in 2013. After that, she was a postdoctoral researcher at Penn State University. Her area expertise is X-ray astronomy of galaxy clusters and supernova remnants. So expert these things. Afterwards, she went to Northwestern, where she became director of operations at Sierra, which I always have to look up what the acronym actually stands for. It's the Center of Interdisciplinary Exploration, Research, and in Astrophysics, where she served as director of operations since 2017. Basically, interdisciplinary group where you have to bring graduate students, postdoctoral researchers, and faculty from all sorts of different branches of astronomy and bring them together as they do large-scale proposals. So she's going to be talking about basically that. We're in this age now where these experiments and these telescope facilities are getting larger and larger. And so you have to bring in lots of people with lots of different areas of expertise in together and get them all working together, and the logistics contain that. So with that, I hand it over to Kari.
Thank you, Ann.
Yep.
Hopefully,
Oh, you got one.
hopefully this works. We'll find out. Okay. So first, thank you for inviting me today. Exciting to get to talk to people who are excited about astronomy, and not just be stuck in the office. Yeah. So tonight, the idea is to walk through how sort of the field of professional astronomy works today, from the people, the processes involved, and some of the different logistics of what makes this possible. So as Ben said, my background is in astronomy. So I did astronomy research for many years, but for the last 8 years, until last October, I was the director of operations for Sierra. And in that role, my job was to manage all the behind the scenes support so that the astronomy could happen, right? So I learned tons of things in that role that I had no idea when I was a grad student or postdoc were really going on. So I wanted to share a little bit of kind of a big picture of how the field works. Okay, so there you go. Okay, so this is kind of the main message, I think, from my talk today. The way astronomy works now in around the world, it's very people dependent. It requires a really wide variety of people that goes far beyond what people normally think of when they think of astronomy and astronomers. It's very interconnected. It requires lots of connections and talking and networks of people and collaboration. The community spans the globe and it coordinates on a global scale as well. And it works over the course of many decades. So it's not a short-term endeavor. Things take a while to play out, and the community thinks on scales of 5, 10, 20 years, or even more sometimes. So during the talk, to try and make things a little more concrete, I'm going to kind of bring up on many of the slides one specific example of a particular discovery. which is in 2017, there was a detected kilonova, which was two neutron stars merging together and then exploding, basically. This is one of the biggest discoveries in the last several decades. You probably read about it when it happened in the headline. There were a lot of researchers at Northwestern who were really deep in the weeds on this. Like my boss was at the NSF press conference and was one of the people who were stood up and talked about it. But it was hailed as the birth of multi-messenger astronomy because it was triggered by a gravitational wave detection and a gamma ray detection of the same event. And that had never happened before. So it involved a huge number of people and was a major event. So I'll bring up examples of this, kind of how this how it worked for this particular discovery. So it led to a gazillion papers, tons of headlines. So there's lots to talk about with it. Okay. This is the roadmap today. So we'll go through the people and the places of who they are, where they are, how do they organize themselves, and how are they supported. And then kind of go through the different stages in the life cycle of a discovery, from the idea, getting the data, grinding through all of the data, how do you share that, and then how that feeds back in to change the future of professional astronomy. So the first thing is the people. This is, of course, the main group that almost everybody thinks of when they think of professional astronomy, is the astronomers. Astronomers come in many flavors. As you likely know, right, there's observational astronomers at all different wavelengths. So I specialize in X-ray astronomy. There are gravitational wave astronomers, gamma ray astronomers, right? And theoretical and computational astronomers who do a lot of simulations these days. And then those who focus on instrumentation, they build their own instruments. Astronomy is a very, just I think in many ways like the amateur astronomy community, professional astronomers are very much a do-it-yourself kind of crowd. We'll just build it ourselves. But there's a huge number of other people that need to be involved, different kinds of expertise. So professional scientists and experts in all different kinds of engineering, in computer science, and different physical sciences, from physics all the way to biology, and even social sciences for some things as well. So it's a really very extensive collaboration. You need all of these people for modern astronomy to really happen at the scale that it does. And it's also very mix and match between a single team or even a single individual will have multiple different expertise, right? A computational astronomer, maybe an expert in data science, right? And a lot of observational astronomers also have a lot of engineering experience because they're building instruments, right? So you need people who have all of this expertise and who are highly trained in this kind of work. To do that, of course, takes a lot of time. So there's a whole pipeline to build this expertise of people who are participating in the research themselves, all the way from high school students to faculty and professional PhD level research staff. But another part of the community, which includes all of you, is the bridge between the general public and the professional science community. So amateur astronomers, citizen scientists, educators at all different levels are really important for building support among the public. It can't happen if the public doesn't support it, or none of these telescopes, nothing. As well as for things like training and inspiring the future generation of all of those experts, right? Even somebody who's interested in astronomy as a kid may go on to do something else that's necessary, like engineering, and for contributing to the science directly as well. So lots of different people involved in this enterprise from all different kinds of backgrounds and walks of life. Many of them are professionals, professional scientists are on the path to being that, but not all of them are. Okay. So the people who are doing the professional research organize themselves across institutions around research goals. So this is often around a shared scientific question or a resource like a telescope or a computing facility or a software package for a simulation. So they organize themselves based on the research that they want to do and the topic and the resources they need to do it. They're very international. So the LIGO collaboration, for example, which made that gravitational wave discovery right in 2017. Is one of the biggest research collaborations. It has around 1,000 scientists, but a lot of collaborations are smaller than that. 18 different countries represented in the LIGO collaboration. And this is the collaboration that takes all of the data from the LIGO telescope, they analyze it, they publish all of the papers, and they work together to do all of that. That is the purpose of the LIGO collaboration. It's also common for collaborations to coordinate and collaborate with each other. So for example, this is the main paper that came out of that multi-messenger discovery. This paper has 3,600 authors, one of the biggest ever in astronomy. What I particularly want to point out is that 26 of those authors are actually named research collaborations, which includes all these logos that you see here, as well as a bunch more, right? So there are, right, SWIFT is a gamma ray telescope, so the people who work on that were involved, right? The Ice Cube Neutrino Observatory, the collaboration that works on that, they were a co-author, right? So there's a lot of collaboration, even among the collaborations, right? So it's very, very interconnected. Am I going off the screen?
Well, just stand over where you normally stand and we'll see if we capture it.
I want to be able to see
We like
everybody.
to, exactly, we like to see your smiling face.
All right. Okay. So the last part of this section of the people and places is the places. All of these people need somewhere to do their work. Okay. The vast majority of professional astronomers work at universities and colleges, government labs, research institutes, and observatories. Almost all of them. So these institutions provide really critical support systems to allow the scientists to do their work. So that includes a lot of people who are not scientists, people who are experts in finance and know how to handle all of the money, for example, communications specialists who know how to write things and translate the work that they're doing, program and operations staff, which is basically what I was, and a lot more. And the institutions also provide other kinds of resources. For example, the faculty at Northwestern who were deep in the weeds and leading this discovery, they needed offices. Their grad students and postdocs needed offices. They needed meeting rooms. They needed Zoom subscriptions, right? Northwestern houses and runs a computer cluster, which is dedicated to analyzing the LIGO data, right? To be able to detect that gravitational wave event in the first place. It runs graduate student and postdoc programs, which admit and train the graduate student who analyze the data, right? Pays the salary of those faculty as well, right? Faculty salary comes basically from the institution. That's not really grant funded. So the institutions that house all of these people provide a lot of support systems. It's really hard for a scientist to just do something on their own in this kind of scale. Okay. So that's all of the people and all of the places. So now we can dive into what actually happened, right?
Okay.
How does that discovery happen? It starts just with curiosity, really. Something is weird in the theory and they can't figure it out. A new instrument comes online, some new technique is developed, which allows them to do something new. Conflicting results, right? One observatory sees something, another observatory sees something else, and they don't make sense together. The physics doesn't make sense. You got to figure it out. Or something weird happens in the sky, which is usually one of the most fun. For this to happen, there needs to be access to prior research, to prior data. There needs to be time for all the scientists to do intellectual exploration, basically, to read, to think about things. But most importantly, it requires interactions. People have to be able to talk to each other informally. So a lot of institutions will have visitors. So visiting other researchers will come and visit. They'll give talks. They'll meet with their colleagues one-on-one and chat about things, share the work that they're working on, right? That's really important. And conferences are a similar thing. It's a chance for all of these people to get together and talk informally and figure out what's going on and get ideas from each other. of course, that's the most common way that ideas kind of happen and things start to grow. Sometimes something exciting happens and it kicks it into high gear. So that's what happened in 2017, for example. LIGO detected something, sent out an alert. The Fermi Space Telescope detected something and sent out an alert. Right? And then all of the astronomers involved in any way had email inboxes that just exploded overnight, basically, right? So this is a quote from one of Northwestern's faculty who does electromagnetic observations at different wavelengths, including gamma ray. And so her email box just went crazy, right? When this happened, they're like, oh my goodness, this changes everything, right? It's tempting sometimes to think that, oh, this is just so lucky that this happened, right? But it isn't just luck, right? The collaborations had to exist. The facilities had to exist and be operational, and somebody had to be operating them. The research collaborations had to be functional. The lines of communication were already established, and they had already thought about what might happen, that this kind of event could happen. What should we look for, and what should we do if it happens, right? So all of that was kind of already in place. So there is luck. You don't know when it's going to happen, but luck favors the prepared, right? So they are prepared. So those are some of the more exciting ones when that happens. Makes them all lose sleep for many months, though. Okay. All right, so now you have data, something happens, you have an idea. It often will take, it takes resources to make this happen, right? For something to actually come of it. So this is often where proposals come in. I would classify them into basically three main categories of proposals. So the biggest is, I call it a major facility proposal. These are usually, think of it as something like launching a whole new research institute or building a big new facility, right? So these are several millions of dollars. They're usually in the US funded by federal agencies, usually NSF and NASA, sometimes DOE, occasionally Department of Defense gets in there. So those are the biggest ones. The next level down is research grants. So these are usually funding to just do the actual work. It's often salary, usually for postdocs or graduate students. So these are, again, often funded by NSF or NASA, are the biggest funders of these kinds of grants. Philanthropic foundations also sometimes do these. For the example for this one, the graduate student who analyzed the LIGO data, they were funded by a research grant from the NSF that their faculty advisor had to propose for. Yeah, so that's how they were able to do the work. The third category is to get data, basically. There are all of these facilities out there, but it takes money to operate them, and the resources are very limited, right? There's literally only so much time on a telescope. So usually the main thing you propose for here is just time. So this is usually, you think of this as time on a telescope, and that's really the biggest one in astronomy. But there's also time on computing facilities as well, and that is getting increasingly more important as the years go by. Sometimes these come with a little bit of money, like a couple months of postdoc time or something, just enough to analyze that specific data, and that's all. But they don't always come with that. Sometimes you just get the data. So those are usually operated through whatever facility runs the telescope or the supercomputer. So the Chandra X-ray Observatory, for example, takes proposals for time on the Chandra Space Telescope. That's what I often used. And those are often underneath a bigger agency. So Chandra's money comes from NASA ultimately, but Chandra handles it. And then similarly for the supercomputing resources, the big ones, right? Frontera is one that's operated by NSF. And Oak Ridge National Laboratory runs one that's funded through DOE. Yeah, so these can be kind of complicated documents sometimes. They require not just the science case. Here's why we should look at this cool thing. The technical plan to prove that it's actually possible to do it with that instrument and how. What is the team? Who's going to do what? What is the budget? How much does it all cost? How long will it take? All of that needs to go into it. So the biggest one I ever worked on, which was in the major facility category, ended up being 800 something pages. Most of that was references, several hundred pages of references, but there's a lot of documentation that has to go into these. There's a ton of work. The smaller ones, like to get time on the Chandra Space Telescope, for example, that might be maybe like 10 pages when you add all the researcher curriculum, CVs and things like that. But ultimately the proposals get submitted, and then essentially a volunteer panel of peers, other experts, get together, scores all of the proposal against specific criteria. Oops, where did it go?
Yeah, probably just got a timeout. You forgot about.
Oh, there you go. I'm talking too long, I guess. Hopefully when I switch things, it will go. Yeah, so basically that committee ranks all of the proposals and prioritizes them based on what they think is the best science case. So what will be the biggest scientific return on that limited amount of resource that's available? And that shapes what gets funded, or which proposals get accepted. Okay, so now we have proposals. We need to actually get the data. So a bunch of facilities are involved in this. So this is the big ones. You all know tons more than I do about telescopes, actually how they work, to be honest. But on the big scale, there are ground-based observatories. I also want to say most professional astronomers do not spend nearly as much time actually with telescopes as probably any of you. They sit at desks almost all the time. Even the ones who use these big telescopes, it's often done remotely.
Yeah, confirm.
Okay. Yeah, so there's lots of ground-based, big world-class, meter-sized kinds of facilities around the world at all different kinds of wavelengths, right? So there's optical telescopes, of course, which people are usually more familiar with. So that's GMT, which is being built. There's infrared, there's ALMA, there's like submillimeter. There's radio, of course, gamma ray, right? Baritone. Ben is very familiar with. And then of course, even things like LIGO, there's neutrino detectors as well, right? So even non-electromagnetic observatories on the ground. These facilities are usually upgradable by design. So some things like the mounts and the main mirrors may be there for decades, but the rest of the instruments are designed to be swapped out pretty regularly. So new instruments will be built often by little teams at universities and then installed on the telescopes. So new cameras, new filters, new spectrographs give them completely different capabilities every few years. So it may have been there for 20 or 30, 40 years, but the instrument, it's not really doing the same science that it was when it started. Even LIGO itself was designed to be upgraded every several years with increasing sensitivity. So every time they turn it on, it's more and more sensitive, and they detect way more events than they did the last time. And that was done on purpose. These, of course, are expensive to build, but most of them are not funded. They're generally not fully funded by a government. They rely pretty heavily on institutional funding like universities and on philanthropy. So it's really a mix. A lot of them are owned privately by sort of consortium-like organizations. And yeah, so you often have to buy into them as an institution. Like, for example, Northwestern has basically had to buy its way in to get guaranteed nights on the Keck telescope, and also has done that now on for GMT in Chile as well. So that's one thing that's very different from these compared to the space-based telescopes. Which is pretty much exclusively what I ever used. Again, they come in many wavelengths, right? Everybody knows about Hubble, James Webb in the infrared. There's UV telescopes, there's X-ray telescopes, and then gamma ray telescopes, of course, like Fermi, which was the source of Wenfei's email explosion in 2017. These often operate for quite a long time. So Fermi has been operating since 2008, and it's still going. Right, Chandra telescope, the X-Men Newton telescopes have been operating for decades. Hubble since 1993, right? So often these are very long-lived. But because it requires a lot of institutional knowledge to build a space telescope and launch it, and to operate it successfully, and they have pretty big budgets, they're usually funded and operated by governments. So this is government scale things. Um, yeah. The other facility that is not as well known, I think, and people don't associate with astronomy is computing facilities. But like I said, that's getting more and more important. Observational astronomy, these new generations of telescopes, are extremely data intensive. The Rubin telescope, which just started operations in Chile and is doing surveys of the sky, it generates 20 terabytes of data every night. So that's the equivalent of 4 million song files every single night. Right, so you have to store it somewhere, you have to transfer the files somewhere, you have to find stuff in all of that data. It is not humanly possible to do that. You need computing power. So that may be on the extreme end, but that is getting more and more common that you really need it. You also really need it to model the data as well. The LIGO data, there are at least a dozen universities and institutions around the world that have computer clusters, high performance computing clusters at their university dedicated just to analyzing LIGO data, right? So Northwestern is one of them, but there's a lot more. So getting the data, doing something with the data and modeling it, all of that takes a lot of computing power. And then of course, state-of-the-art simulations require really, really powerful computers. So they can take hours or days even on the fastest supercomputers in the world, right? And for theoretical astronomers, that is the telescope, that is where the data comes from, right? So you need them for that. So there are both these big, big national level supercomputers, which are kind of like best in the world, which are really competitive, and then smaller ones at institutions to do more of the day-to-day work and to test things and develop the software and the simulations on a smaller scale. So all of these are very big projects, right? As you can tell, there are usually hundreds of thousands of scientists all over the world who are supporting these facilities and using them together, who are not employed by the facilities themselves. Often the technology doesn't exist until it's built, right? Developed for this new thing. So they have to build custom stuff all the time. It takes many years to design these things, to plan them, to construct them, and then they operate for a long time usually as well. So all of that basically means that most of these require governments to be pretty heavily involved in some way. And so the really big facilities like this, there's not that many governments actually that have the capacity, sort of the infrastructure and the knowledge and the funding to do this. So the ones that you see here are basically those. But even they often work together. So you can see the kind, how many they do at any given time. There's maybe a couple in the pipeline basically. And the timelines for those are decades. So it could be they're in development now, but they won't actually come online for 20 years. Right, so this is long time scales. And it varies depending on the specific project, of course. But partly because of this kind of big scale, there has been a growing movement to use sort of a complementary approach to go along with these big projects. So I'm going to call those nimble projects. Basically, it takes two main forms. So the first has been around actually for a fairly long time, which is basically to take advantage of smaller telescopes and the much bigger community of people that has those and knows how to use them. So that's things like small observatories that are used for education and for public outreach often, like your observatory, actually, to train scientists. So that's how I got my start. My first research was done on a 12-inch telescope monitoring for variable stars when I was an undergrad. But you learn really important things, just technical knowledge of how to do it. And then also to use those same telescopes to actually monitor the sky and take observations, right? So the Kilonova Catcher program, for example, is a way for amateur astronomers and people with smaller telescopes to actually do optical follow-up of gravitational wave events to help find the next kilonova that might be the next big thing, right? So you sign up for the project and then there's all sorts of instructions and things for how to help contribute to the data. And then moving away from the telescope, you can, if you just have a computer, there's more and more use of basically citizen science projects. So for example, Gravity Spy was a way for anyone with a computer to sign up and help classify visually basically the types of noise in the LIGO detector. So by characterizing the noise better, they're able to detect more real events and be more confident in those detections. So because they knew the noise better, they had smaller confidence margins, and you can detect more things like that thing in 2017. Okay, so the second main form of this sort of nimble project is a little bit newer. It's basically to be faster, cheaper, and iterative. So it's lower cost. It does that partly by using more off-the-shelf components, having building facilities with narrower science cases, because that allows you to do things on a little bit smaller scale, but it also means they have shorter lifetimes. So there's a cost in that the things don't operate for as long and you can't do as much science, but you can do it a lot faster. These often depend a little bit more on philanthropy funding than the government, because this is at a scale that a philanthropist can do more easily. One example of this kind of project is the Mothra telescope, successor to Dragonfly. Astronomers are sci-fi fans often. But this one basically, it uses cameras and filters from commercial manufacturers, and it's combining them into arrays and putting them into a single observatory, basically to create a world-class observatory using all this commercial equipment, right? So it's technology that's been driven basically by the amateur astronomy and astrophotography markets. And they can put it together, and now they can build a world-class thing in Chile to do new kinds of work. So it's yeah, so keep taking more pictures. Ask the manufacturers to do harder and harder things. It helps, it helps. So neither of these approaches replaces the big projects, right? Like you can't detect gravitational waves with something you can buy off the shelf, right? It just doesn't work. But it's a really important complement, and it's becoming a little bit more common to kind of try and find ways to do this. So, okay. Now we have the data. The next step in the cycle of discovery. You have the data, you have to do something with it. So first you need some tools. You don't buy software to detect a black hole. So astronomers in the do-it-yourself attitude that we tend to have, build their own automated pipelines, come together as a community to build shared software libraries and different tools, make shared data archives, right? And once you have all of that, then you can start to analyze the data. So the data analysis pipeline, and this could be simulated data as well, like a similar steps apply. So that's it's very important to be able to compare it. So it often looks like something like this. So first you've got to clean up all of your data. Once you're satisfied it's clean, apply some statistical analysis, do some modeling of the data, and then try to figure out what the heck it actually means, basically. So you might compare what you expected from theory to what your observations saw. You'll compare different observations to each other, right? Across wavelengths is especially useful because it tests different parts of the physics. You visualize things, try to figure out what physics can explain the data that you have. Of course, it doesn't ever go that cleanly. It's not nice. Step 1, step 2, step 3. Okay, now move on, right? You constantly have to go back and fix things and redo things and reanalyze and re-clean your data because they released new calibration software, right? How many different versions of the X-ray analysis calibration software did I have to install? Yeah, so it can be kind of messy, right? This is not a linear process. But ultimately, the revelations that you get, it's not like some sudden light bulb, like, now I have it, right? You have to really carefully do everything. You have to test things. You have to check it. You have to do the statistics. You have to know your confidence margins. You really have to do the math to get out the other end, something that you're like, yes, I have measured this thing and I am confident in it. Now I can check the physics. Okay. This is kind of the day-to-day of what people often think of. This is kind of what I thought of when I was younger. This is doing the science, right? There's another important part of it. Remember I said science is that this is a human endeavor, right? And it's very collaborative. So it doesn't happen by yourself. It's not just one person doing that, okay? So it's a lot of working together with the people in your collaborations, real-time collaboration, virtually, right, via Zoom and Slack messages and email and all kinds of things, as well as in person across many time zones usually. Yeah, so just kind of try and visualize this a little bit, thinking back to that 2017 discovery, right? LIGO data rolls in, some grad student is assigned to do the analysis of the data when it comes in. They sit down and they do that. And then they share those results, what they initially got with, say, their faculty advisor, right? And then they share it with the LIGO working group in the collaboration who's in charge of the analysis. They talk to each other, they debate, they ask a bunch of questions, they test things, right? Then they share it with another group who did the same thing independently, right? And then they keep sharing it outward with ever larger groups within the collaboration. At every single stage, everyone is trying to poke holes in it, right? Have you thought about this? Have you thought about this? I don't believe that. Try this other technique, right? Every single stage. And it keeps getting bigger. And in the case of the 2017 discovery, once the LIGO collaboration was satisfied with it, you can't write up that paper with 3,600 authors until the other authors get their say, right? So then you have to go out to the other collaborations and get their input as well. So everybody is trying to figure out how it can all make sense and make sure that this is really robust. And sometimes you have to consult with specific specialist people that may be outside the group if you need to. So it's lots and lots of hours, many days, lots and lots and lots and lots of discussion to be confident in what you're doing. And to share the expertise, right? Everybody in the group has different expertise and knowledge and from the work that they're doing. This is part of the interdisciplinary part of it, right? If somebody's trying to apply machine learning algorithm to something and that somebody else who's actually more of an expert in that comes in and says, actually, you did that wrong, right? You want to know that before you write it in the paper, right? So it's really important. Okay, but let's say this all goes well, but again, not a linear process. Go back and start over and do it again, right? That kind of thing happens. But eventually it kind of comes to a consensus. People are satisfied, like, yes, this is really good. We know what we have. We're ready. Now let's write it up and share this with the world. Okay, so the publication step is really important. This is the only, it's really the way that adds to the body of knowledge. Remember I said earlier, when you have to get ideas, you need access to prior research and data. This is the main way that happens. And because it goes through all of this iterative process and all of these steps of review, even before it gets to the submitting to a journal part, that helps it be more robust and make sure that the things that are there are really useful and worth adding to the body of knowledge. So the first step in this, once the group is convinced that, yes, we're ready to write this up and submit it, then there's a lot of work in just among the co-authors, talking to each other, writing, revising over and over again the draft, making sure it makes sense. How do we say this? Is that really what we want to say? Getting the visuals all in place, the graphs and everything. And then once they're happy, it gets submitted to a journal. So once that happens, so in astronomy, there are actually relatively few number of journals compared to a lot of other fields. A lot of them are run by the professional societies themselves. And at the journal, an editor will get every submission and will recruit a volunteer peer reviewer. So this is other experts who are qualified to assess the content of that specific paper. And they review it anonymously for free. Takes a lot of time.
Browbeat.
Hmm?
I'd say draft or browbeat.
Yeah.
Yeah.
Yeah, they recruit. They have to be very good at recruiting and figuring out how to get people to do it. But it is a really important part of the process. So they get a peer reviewer, and that person writes up a whole bunch of comments, again, tries to poke holes in it, but also sees, like, is this, even if it's fine and there's like not any errors in it, it still may not necessarily be worth publishing in that particular journal. And so they would make their recommendation, but usually they'll have a bunch of questions and, things they think need to be changed in the paper, improved because it's not clear or whatever. It gets sent back to the authors, goes around and around again, gets revised, sent back to the journal. And that can happen a couple of times. I think if it comes back to the authors a third time, that's pretty rare. It could happen, but I don't know, I haven't heard of it happening that much, but it could happen more than that. It's probably not a good sign. Yeah.
This brings to my mind, a lot of what I see, when, articles from this brings to mind a lot of what I see in articles from Scientific American or talking about something. They often they'll throw in a comment that is stated by a professional who was not part of the process.
Yes,
You know,
journalists always do that.
See this process at work.
Yeah, I think it's for similar reasons, right? You need somebody else to look at it who knows what the heck they're talking about to be able to say, yeah, this is real, or you know, it is really important. And often, I mean, having been on both sides of this process myself as a scientist, it can be quite stressful. But the paper always does come out better on the other side of it. Like because the person who's doing the review really wants to make sure that the science is good. They don't like want it to fail necessarily. Maybe some of them do. Right, but they want it to be good science because it will help them, right? It's sort of like the rising tide lifts all boats kind of thing in some ways. If it's poorly done, it is bad for the field, right? So they want it to be good. So it often does come back better. You realize, oh, actually, that was a horrible way to explain that. It doesn't make any sense, right? Or, oh, I didn't think of that thing. I better go check that. That's a really good point, right? So it's a really important part of the process. And hopefully after a couple of iterations, then the reviewer will be like, yes, I'm satisfied. I recommend this for publication. And when that happens, then the editor will schedule it for publication. And then it gets published. So one of the things I wanted to also mention as part of the publication process, a lot of astronomy has been pretty strongly moving towards this open science framework. And so all of the American Astronomical Society journals, for example, which are the primary journals in the US where things are published, they have all been open access since 2022. So that means anybody can access the full article and all of the things that go along with it without needing to have a subscription, right? So any of you could go to any of those articles and just look them up and read them. It's also getting more common for journals to require public archiving of all of the data and any of the software that was used, the specific versions and everything of that software that were used to do the analysis in the paper. So that's getting more common as well. That's part of this kind of open science movement. And then in addition to that, and this has been happening for a long time, the authors will post on the archive website a copy of the paper. So the authors are allowed to do that as the authors. Usually they'll do that when it gets published. And that basically functions as the news feed for all professional astronomers. A lot of them check it every day just to see what is the latest papers today. Because it's very fast, it's easy to browse, and then they can see what are all the latest things. So, yeah, so open science. And then at the same time, as all of this is happening, if it's something of particular interest that the public might really want to know about and read, while the paper is being reviewed and drafted, the researchers will also often be working with teams of professional science writers and people who know how to do graphic design to prepare things for the press, to make a public announcement, because you can't just throw the scientific article to a journalist and say, here you go, announce this, right? It will never work. And scientists are not always the best also at translating their work. I think astronomers are often better at it than many other kinds of scientists, partly aided because black holes are just in general cool and easier to visualize than some things, but it does require sort of specialized expertise to help work through this, right? When the 2017 kilonova discovery was going on, between August when the detection happened and October when there was the actual announcement and release of all the discovery, there were just hordes at all these different institutions of, and at the NSF as well, right, of journalists who were writing, preparing articles, graphic designers making interactive visualizations and cool images, right? There were people making videos, interviewing all of the researchers, right? So that once the stuff became public, then there was all of this material so that the public could immediately engage with the discovery. So that all happened kind of in parallel. That doesn't happen for every single paper, right? Like there is a filter because not everything is that much of interest to the public, even if it's really important and of interest to the professional astronomy community. So, but if there is that much interest, then that work also goes into it, and it's timed with the publication date of the paper. Okay, so now we're done. The discovery has happened. Hurrah, we're successful. Astronomy done. No, okay, so every time there's a new discovery like that one, it leads to all kinds of new questions, right? Which then the community wants to answer, right? But answering all of those questions requires coordinated long-term planning and investment, right? Which the astronomy community does on actually a fairly organized, in a fairly organized way. More organized than it might seem. So the major way this is done in the US is through what's called the decadal survey. And there are other ways this happens, but this is sort of the most organized and the most well-known way. So it's a good example. So in this process, it's a national process organized by the National Academies of Sciences. And all of the community comes together and debates and argues and tries to advocate for what they think should be done in the next 10 years in the field of astronomy. And it starts by figuring out what is the science that we want to happen in the next 10 to 20 years. What are the big science questions that we think are the most important to answer and that are realistically can be answered in the next 10 to 20 years. So once they have those goals, then they make recommendations for what investments need to be made so that we can do that. The kinds of investments that are made include things like flagship facilities. For example, in the 1980s, a decadal survey recommended LIGO be built. And then a few years later, the proposal to construct LIGO was approved. If that hadn't happened, there may not be a LIGO, and there would have been no kilonova detection, right? There would not be multi-messenger astronomy as there is now, right? And that was how many decades ago, right? But it was in a decadal survey that said we should do this, so that helped. So there's tons and tons of, there's lots of white papers. People come, astronomers and other scientists come together and say, we think we should fund this. No, we should fund this. Here's what needs to happen, right? There's town halls at all the major conferences where everybody gets together and talks about different things. It takes a whole year. And then in the end, you get things like recommendations for the big facilities. You get recommendations for what kind of technology development is needed. What would it take to develop the technology that's necessary? What kind of timeline would that be? What infrastructure is needed? Do we need to build more archives for the data? Do we need certain software? What do we need? And as well as workforce. Remember, there's that whole pipeline of all that expertise that takes years to train them. So it thinks about what is a way to provide a stable career pipeline so that by the time this new stuff comes, there are people who have the training needed to actually do something with it, to operate that telescope, to analyze that data, to write that software, whatever it is. Yes, the forward one. So now this particular discovery, right, it helped the field realize the possibilities in coordinating electromagnetic and gravitational wave observations. So that got explicitly then put into the 2020 decadal survey, right? So that discovery, this is partly how it shapes then the next 10 years in astronomy, right? It goes in there as a priority. Yeah. If we want to study more, we have to be ready to study. We have to be ready to find them. And the other thing that's in here is this particular 10-year kind of roadmap explicitly emphasized the importance of public engagement to maintain support and funding essentially for this kinds of investments. And that is one of the ways that I mentioned earlier on that people slide. Remember the bridge community, which is all of you, right? Educators, citizen scientists, amateur astronomers, because as professional astronomers do not always good at engaging all the different kinds of people that there are in the public, and we cannot be everywhere, right? And so it really, really takes more capacity. You just cannot engage the public at scale, as much as professional astronomers try. Like we've held public lectures and do all kinds of things, but you know, there's a few thousand professional astronomers maybe in the US, right? It's a limited capacity. And honestly, even if we go out and talk to them, I can't look through a telescope. Nothing excites people about astronomy more than actually looking through a telescope with their own eyes and staring up at the sky with their own eyes, right? I don't know how to use a telescope. I should have do that, right? A lot of astronomers can't. Even if we could be in every town, we still can't do that, right? But I mean, that's how I got started to begin with, right? It was by stargazing. I standing in my snow boots in the front yard as a kid. Yeah, so it is a very big community, and it takes everybody. And that basically brings us to the beginning, right? Back again. So now this giant people-driven interdisciplinary endeavor, right, that is astronomy, can continue for another decade, hopefully many decades. So that's the discovery cycle in astronomy, in professional astronomy. How it works. Happy to take any questions anybody has.
You mentioned there's kind of a iterative cycle where the current capabilities then feed into the next decadal survey. Thank you. You mentioned there's an iterative cycle where the current capabilities feed into the next decadal survey, which then drives the next instruments, observatories that get engineered, built. I was wondering, when you look at something like, say, LIGO, and then some more electromagnetic observatories, is that kind of what happened with the laser interferometer space antenna? I've heard of that, like ambitious project to try to do LIGO in space. Was that sort of like, because we had LIGO and it's ground based, like, well, you know, what if we combine the space observatory aspect, but use laser interferometry to measure gravitational waves? Is that kind of what happened there? Because I always wondered how that came about.
Partly, yes. So I think the size, there's multiple reasons they wanted to do it in space. So I will say that once LIGO actually detected gravitational waves, which, I mean, I didn't necessarily believe it could happen. A lot of astronomers even were like, that's never going to happen. Like the engineering challenge required is so ridiculous, it's never going to happen, right? But once it did happen, that helped get more support behind LISA, right? Which is the space-based interferometer. So that did have an effect, because now suddenly it's possible, and you realize, oh my goodness, we can actually do this, right? And then I would say the part of the reason that LISA was also kind of put forward and has support as well, because it does different things. It detects different things than LIGO will, because the size is different. It's essentially something like, for electromagnetic radiation, you have optical telescopes and you have gamma ray telescopes, right? Like there's a spectrum. It's the same in gravitational waves. So because the baseline is so much bigger in space, so you're going to detect different kinds of objects than you would with LIGO. So it's kind of like, okay, now that we can do, like, we can do this. Can we broaden the spectrum? Can we add the equivalent of, gamma rays? Or maybe it's the other way. I don't remember. I never remembered the frequency, which one's longer, but yeah. So it did help for sure, because now we know we can do it, and there's so much potential here. So it helps get more support behind it.
One thing I didn't see mentioned in here, and hopefully you can kind of elaborate, but where do you see artificial intelligence perhaps fitting into this cycle, and how will that maybe shorten your cycle time?
There's a bunch of possible different ways that that 800 something page proposal that I mentioned, that was actually for an astronomy AI institute. So I got to sit in on lots of conversations about astronomy and AI. So one of the ways that it will help is there's a lot of potential ways, and some of them they're just exploring now. But one of the ways is actually something that has been done for a long time. They just weren't calling it AI; they were calling it machine learning, data science. But it's basically to figure out how to analyze larger amounts of data faster and find things in the data because it's pattern recognition essentially. And so there's a lot of work going into basically using AI to speed up the process of analyzing the data and finding new things. So finding specific categories of things, finding things that seem to be real events but don't match anything we've ever seen before. And that will save a lot of time. And there are ways that AI can kind of shorten how long it takes to do that compared to just more traditional kind of coding where it's just cranking through it in a more methodical way. There are also things like on the theory side, they're talking about ways to use AI to essentially speed up simulations, basically. So it takes, or I say it can take hours and days for simulations to run. And the more complicated physics you try to throw into that, the even longer it takes. And that's extremely constraining because there just aren't that many big supercomputers, right, that can do it. So if you can reduce the amount of computing power by using AI to do it and add more physics, then you can do more informative simulations. So they're trying to find ways to kind of use AI to kind of enhance or replace parts of the simulation process very carefully. There's very much concern about making sure that it's kind of interpretable and that you can scientifically trust the results for that kind of thing, but they are thinking about it.
I have a question. I was impressed by one of your slides early on in this talk where you talked about the number of big projects again in Europe
Mhm.
and then China and the US right on that. Is the US really keeping up? Are we falling behind or is Europe just, have they just
Mhm.
taken off recently and accelerated their?
I think, I don't know that I would say that Europe has accelerated their research. Partly there's more there because, I mean, there's just more countries contributing. So I couldn't actually break that out by country because almost none of them do anything by themselves for this kind of scientific project, right? So there's like the European Space Agency, for example, which funds a bunch of and operates their space telescopes. And there's almost always a bunch of different countries coming together in Europe. It's not always exactly the same group, but they don't do things alone. So because there's more countries involved, then you can do more things, right? So it's partly that. But China has also been ramping up quite a lot in what they're funding. It's hard to know always exactly how much they're doing and what they're doing and how much they're spending, but they are developing a lot more things. They're really investing a lot in astronomy right now, and the US is not accelerating at all, right, in their investment in astronomy. And so I don't know if we're necessarily falling behind yet, but definitely at risk.
I didn't know if it was just due to funding being cut more recently, so take on these big projects or that had anything to do with it.
Partly for the bigger projects, I'm trying to think what bigger project, if they're bigger, well, LIGO itself was under threat, actually. There was some things going around about wanting to shut down one of the LIGO detectors, actually, which you can't do it with one, like there's a reason you don't do. It also wastes all of the money that went into it in the first place, right? But one of the biggest threats actually is not for the big facilities necessarily in the US right now, it's in the people. Because it takes so long to train all of the people, and once you lose them, they're gone. If they leave the field of professional astronomy, they're out. Very few people ever come back into it. And so if you can't train them from the beginning and keep them there, you lose it. And then suddenly you don't have people who know how to operate anything, who know how to do the analysis, right? So you risk losing the people who you just spent decades training. That's the risk.
Gary, just sort of, add on, got it. Wasn't, just to kind of follow off that question, wasn't, observatories like, I seem to remember Chandra being at risk and Swift and the other X-ray observatories? Are
Yep.
they still going or
They
what's that going on there?
They are, Chandra, I don't remember the latest news on this, but so don't quote me on this, I'd have to double check, but I think the plan is that they are going to be winding Chandra down now. And there's not really a replacement for that, so the X-ray telescope, the US runs will go. Swift, I don't remember that one. But it's, yeah, so some of them that they're more at risk to being
Okay,
decommissioned and wound down, I think, but I'm not sure how many of them have been actually for sure, absolutely, this is done. So I think everything is kind of at risk right now.
right.
The bigger facilities are taking, there's a risk there.
Yeah.
So,
Just to, can follow up, can you, because not many people in the room have expertise in X-ray astronomy, can you kind of speak for a moment, like the importance of Chandra and like the other observatories, Swift, for example, if you, like
yeah.
what their importance is to the community?
Well, X-ray astronomy is one of the wavelengths that you just cannot possibly do from the ground. Right? You must have an X-ray telescope to do it. There's no other way. And Chandra is, I could never have done anything actually without that one. And the Europeans have one as well, which is complementary to it. But one of the things that I studied, right, it was the closest supernova we've ever observed. And because it was so close, it means you could see it for a long, long, long time. Never had the opportunity, right, to be able to see not only picture of the star, now we see the supernova, and now we see what the heck happens and how it evolves until it becomes a supernova remnant, like these big, beautiful, cloudy things, which are. But we've never seen it go from one to the other, right? There's never an opportunity. And the X-ray space telescope, I mean, those things are hot, right? A supernova has a ton of energy, right? It just plows itself out into the surrounding gas. And you learn so much about the physics from looking at the X-rays. What is the spectrum? How hot is it? Is it a power law? Is it not a power law? What elements are there in the supernova? And then what elements are in the surroundings? And you can only do that by looking at the X-rays because that's what it's emitting. So if you can't see the X-rays, you can't tell what it's emitting. You don't know what's going on. It would have been gone. And Chandra was special because it has relatively high spatial resolution for an X-ray telescope. And so you could actually was the explosion going outward and propagating out. And so part of what I was doing was I was taking my turn, so it had been monitored since Chandra was launched, and I was there in 2013. I came online, so I was, a decade into this. But to see how is it growing? How is the ring changing? Is it brighter over here? Is it brighter over there? Are we seeing different emission lines, different elements popping up? And how happened and what material it was in, and yeah, you can compare it with Hubble. Actually, it had enough resolution, you could actually look at it and see how does this line up with the Hubble images, and with no Chandra and no replacement, we will not have that anymore.
When is that gonna go bye-bye?
I'm not sure what the date will be. I have to double check that one. I have not looked that up, but
Somebody's got a plan for maintenance upstairs, huh?
no, most of the space telescopes are not ones that are maintainable. China says they're going to launch a optical one. I think I saw something that is supposedly going to be something that they can actually go in and fix it and upgrade it
And
and
the
stuff.
Europeans, are they more European community or the Chinese, are they more sustainable in their astronomy efforts? Because my perception of the United States is, man, we love a big splash, man, shoot up or the moon, yeah. And then it's like when Chevy Chase goes to the Grand Canyon, it's like, no, yeah, I saw that, let's go. No. So we're after we get to the moon, it's like, yeah, whatever, okay, so.
So sustainable in the sense that like, will they keep going and keep investing kind of
I mean,
at this rate?
you did the X-ray telescope, right? I mean, it's sort of like buy a car, and then when your car gets older, you buy a new car or a newer car, right? Nobody in the family says, wow. No, you don't need to buy something. Like, I mean, but as a country, it seems kind of bizarre because, if we think we should do this research, obviously you need a continuous. I mean, suppose we kept going to the moon, even like, I don't know, do a mission every couple of years, and now you don't have to re-crank up, you had all these people that were trained and could figure out, and then they just mothballed everything and stuff, and so now we're gonna do it again, but I feel like it's more of a, like NASA in some essence is becoming a little bit of a circus act, like, it's like, yeah, great, super.
It definitely does matter. The X-ray astronomy community is for a number of years been concerned actually because there will be two things lost, I think. And this is just one example, right, is the X-ray astronomy. And one of those things is that the people who know how to build and operate an X-ray telescope, the ones who built the last X-ray telescope, right, this thing was built in the 90s. It was designed in the 80s and the 90s, and right, those people are going to be retiring. That knowledge is going to be lost. And if you don't have anybody who's been using it and, who knows the technicalities of how that thing actually works, then you have to kind of start over. And then the second thing is that there will be a gap. You can't do astronomy with one wavelength. It doesn't work, right? You need them all, as many as you can possibly get, right? But you can learn things with X-rays you cannot learn with anything else. And it multiplies on itself, right? So if you have just X-ray and just optical, it's not just double. Then you add radio in there of the same thing, and you look at the same thing, you learn even more, right? It's not just a linear thing. So for supernova 1987A, for example, Chandra goes away. Okay, we can still monitor it with, whatever, James Webb, and maybe Hubble still be up there, right? Continuing. The radio observations can still look at it, but 20 years go by, we've been monitoring this thing for decades, and you're gonna have this huge gap when interesting stuff is happening, and maybe the X-rays could be the thing that tell you
So
this is the physics.
The Europeans and the Chinese are filling in the gap where they are.
There's one X-ray mission that the Europeans are working on, but it won't quite fill the gap because there's trade-offs always, right? So what had been, when I was being trained, there was XMM Newton, which is a European Space Agency X-ray telescope at Chandra. And they had different capabilities, right? So Chandra had really good spatial resolution. XMM had sort of like a wider field of view, and some other things that Chandra couldn't quite do. And so with both of them, you were good, but they're both aging out now. And so even if the Europeans build one, it's not going to have the spatial resolution that Chandra has. I don't know that China was building X-ray one necessarily. They might though. I would not be surprised. We'll see if they can sustain it though. That your original question. I don't know. They're pouring a lot into it right now. They say they're going to do a lot of new things, and they have been doing new things, like they're building giant radio telescope, for example, right? It remains to be seen how much they really sustain that. If they do, and they can start building real long-term capacity and knowledge, then they'll keep going, and they will probably surpass anybody who doesn't try to keep up.
Isn't it more of a kind of a cascading problem too? If the technology, the equipment ages out, there's less tools. What does that say for people who might have gone into that as a career when those tools aren't there? So you kind of snuff out the pipeline, right at the education level, and that's generational that you've lost.
Yeah, yeah. That's why I think that really the biggest risk isn't necessarily the facilities. In thinking of those proposal levels, I think actually it's the research grant proposal level that is the biggest risk to astronomy, because that's the one that funds the people mostly. If you don't have people, you can't do anything. You lose your pipeline, you have this generational gap. So that's what I'm personally most kind of concerned about. And a lot of astronomers are talking about that too, that we're gonna lose a generation, right? If we're not careful.
Any other question? I just have one more question to ask you. Could you sort of give us an update where this Magellan telescope is at now down in Chile?
Yeah.
This Northwestern's been heavily involved.
Yes. So the mirrors, I think, are constructed. Actually, I saw part of it being constructed once a few years ago in Arizona. They were constructing the mirrors. The site is under construction, and it had passed. I'm trying to remember the name of the development stage, but it is progressing. And so I think that is on track for, what was it, 2027, 2030? I never remember. Well, one of the faculty that I work with who's done a lot of instrumentation, he's retiring soon. He's like, yeah, instruments are always 3 years away from being done. They're always 3 years from being finished. Until you get within 6 months, and then you can say, okay.
But the aperture is like 25 meters.
It's big. Yeah, I did a mock-up of it once actually. And I think the people at MIT, I think, had done this too, to see like, so the building for it, oops, let me go backwards. I mocked it up inside of Northwestern's, yeah, so that's it. So you can see here, right? This is the mock-up to scale. So you see the little cars down in the corner, right? That gives you the scale. So basically, I had like tried to roughly scale it correctly and plopped it down in the middle of Northwestern's like football stadium, and it basically takes up most of the field, the building. But it is on track to go. So it's it does. I think that they are still working on and kind of needing to get a little bit some funding from the NSF, and I think not all of that is fully secured yet.
It's like a $2.5 billion project.
It's a lot.
Yeah.
So I mean, for a university to buy into this, I mean, it's tens of millions of dollars, or more, depending on basically how much control you want and how many nights you want.
That's exciting. Yeah.
Yeah, but it's going. It has an edge over TMT, which is nice for us.
Nothing else here? Well, thank you so much for just a terrific evening. I tell you, just it was so interesting hearing you talk. And we appreciate you bringing your family all the way down from Chicago also, and making the effort. So can't thank you enough.
Well, thank you for inviting me. I don't get to talk about this often.
You have this star, which is in gravitationally locked to the black hole Cygnus X1, and this zooms in on that. This right here is a visualization of what would look like if you could be there. I mean, out and out close. So the distance between the black hole and a supergiant is about the distance of the solar system, right? So this is a kind of just a visual representation. And then these right here are my reference stars. You have HD 189, 148, and Eta Cygni, which don't vary. They're stable. So you input into the program their magnitudes, and based off of that, it'll tell you the magnitude of this. And this right here is showing the magnitude change over 3 days from 9.023 magnitude to 9.06 back to 9.023. And that right there is the effect of tidal gravity, which shows that, all right, in a 5-day period, the difference wherever the black hole is in relation to the blue supergiant, you're going to have that, it's going to affect the brightness of that blue supergiant.